3, Section 2.1. Now we're going to talk about graphs of basic functions and relations and symmetry. Continuity, an informal definition of continuity is a function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. Discontinuity is if a function is not continuous at a point, then it may have a point of discontinuity or it may have a vertical asymptote. In either case, the function is said to be discontinuous at the x value. For example, the graph on the left, if we were to draw it, would come this way. Then we have to pick up our pencil and draw the graph this way. This graph is discontinuous at x equals 2 because we had to pick up our pencil to move from one to the other. This one, the graph goes all the way over this way and it gets closer and closer and closer to 2 here. And then here it starts way down here at 2 and then it gets further and further this way. Both of the graphs we had to pick up the pencil. Therefore, they're both discontinuous functions at x equals 2. Now, determine the intervals of continuity. On the first graph, on A, we could draw all the way to the left and all the way to the right, and really we would never have to pick up our pencil. Therefore, the continuity on this one would be from negative infinity to infinity. Now on point B, you notice that on graph B, you notice this open circle right here. That means the graph goes all the way this way, except at 3 it's not included, and then it goes all the way this way. So on B, the intervals of continuity is it's continuous from negative infinity up until it hits positive 3. And then we union that with at 3 all the way to infinity. And then number C, that one the graph goes all the way up until we hit negative 2. Then it comes all the way down, but at negative 2 there is no value. That's what that little vertical line means. So same thing, we'd have a negative infinity up to negative 2. Remember, we use parentheses because it does not actually include that point. And then it starts back at negative 2 and goes all the way over to infinity. Now, suppose that a function f is defined on an interval I, and I is just any interval. F is increasing on that interval if whenever x1 is less than x2, f of x1 is less than f of x2. And what that means is as your x's get larger, the f of x's must get larger also, or the graph is going up from left to right. So increasing functions mean as the x's get larger, the function values will also get larger. Now, same thing. Suppose that a function f is defined on the interval I. F is decreasing on I if whenever x1 is less than x2, that means your x's are still going from smallest to largest, f of x1 is greater than f of x2. So what that means is if the x value is smaller, then the function values have to get smaller as the x's get larger. Or the easiest way to look at that is if your graph is aiming downward, then it is decreasing. Constant functions. Suppose that a function f is defined on an interval I. F is constant on I if for every x1 and x2, f of x1 is equal to f of x2. And what that means is it does not matter which two x values you pick, their function values or their y values have got to be the same, which basically goes back to our constant function that looks like a horizontal line. So let's do one. Determine the intervals over which the function is increasing, decreasing, or constant. So if you notice over here as the x values come from left to right, your graph is really going down, even though that arrow is going up. Coming from left to right, your graph is going down, so we say that it is decreasing on the interval negative infinity till 1. Now remember, we're using x values. It did not include a 1, so we put a parenthesis on 1. Then you come over here and you say, well, the graph is now going up, starting where x is 1, all the way up to where x is 3. So we say that it's increasing on the closed interval from 1 to 3. And then starting where x is 3, the y values stay the same, so we say that it is constant on the interval from 3 to infinity. Okay? Now, what if they don't give us a graph? Over the interval specified, tell whether this function is increasing, decreasing, or constant. Now, do you remember what an x to the 4th function looks like? Maybe not. If not, then what we're going to do is we're going to go on our calculator and we're going to graph this. We're going to go y equals x to the power of 4. And we'll go back to Zoom 6, and there's our picture, okay, which says we've got a graph that looks like this. It's sort of like the x squared graph, okay, and this little point right here is 0, 0. So coming from left to right, as you're coming across the board, these x values are going down. So we say that it is, decreasing from negative infinity up to 0. And then it starts back up. So we say that it is increasing starting where x is 0 all the way to infinity. Is it ever constant? No, there's no place on that graph where it actually is a horizontal line. Okay, let's do another one. 2 plus x squared. If you remember how to graph 2 plus x squared, graph it. If not, we're going to go in our calculator, look at our picture. We've got 2 plus x squared. Graph that. That says that we have our parabola up 2 places. So we're going to have a graph that goes over 0 up 2. And then we're going to have our little x squared graph on there. And the vertex is going to be right there. Same thing. Coming from left to right, it decreases until x is 0. And it increases, whoops, sorry, I went the wrong way. It decreases from negative infinity to 0, and then it increases from 0 to infinity. Now let me go back and read the problem. It says determine over the interval 0 to infinity, so we're only looking from 0 up this way. Well, for all of these x values, that graph is going up, so we say that it is increasing on that interval. Let me back up. What about this one? Over this specified interval from negative infinity to 0, in this interval, that graph is going down, so we would say that this function is decreasing. Okay, now let's talk about some basic function types. First type is called the identity function, and that looks like f of x is equal to x. Or if you think back to old stuff, y is equal to x, which means whatever x is, that's what y is. if you plug it into your calculator and look at the table, whatever x is, that's what y is. If you graph it, it's going to be that line right up through the 45-degree angle. Now, f of x equals x is increasing on the entire domain, and it's also continuous on the entire domain. We never have to pick our pencil up to draw it. Now, the degree of a polynomial function in the variable x is the greatest exponent on x in the polynomial. That is, the degree is the highest power of the x. Now, if the degree is 1, the function is linear. If the degree is 2, the function is quadratic. And the simplest quadratic function is called the squaring function. And if the degree is 3, the function is cubic. So the simplest quadratic function is f of x is equal to x squared. Over here on your calculator, if you plug in x is 3, you get 9. If you plug in x is -1, you get 1. If you plug in x is 1, you get 1. The graph looks like this little parabola. It starts at 0, 0, and it goes up real fast in both directions. Now, the squaring function, x squared, is continuous on the entire domain from -infinity to infinity. It's increasing from x is greater than or equal to 0, and it's decreasing for x is less than or equal to 0. Now, when the graph is called a parabola. The point on the graph where it changes from increasing to decreasing, which is this ordered pair 0, 0, that is what we call the vertex of the parabola. Okay, now we're going to talk about symmetry, which means same. If a function f is defined so that f of -x is equal to f of x for every x in the domain of the function, then f is said to be symmetric with respect to the y-axis. Okay, the easiest way to think of this is if you have a graph and you can fold it, if you put it on a sheet of paper and you can fold it down the y-axis and get the same thing on both sides, then we say it's symmetric with respect to the y-axis. If f of x equals x squared, to show that it's symmetric with respect to the y-axis, the first thing is we're going to do is plug in, there's your f of x, which is x squared. Then we're going to plug in f of -x, which means -x squared, but -x squared means x squared. So did we get the same thing for both functions? Yes. So we say that this graph is symmetric with respect to the y-axis. Okay, or same thing, if you look at your picture and you fold it right down this y-axis, would the graphs overlap? And the answer is yes. Now, as a note, in general, if a graph is symmetric with respect to the y-axis, then the following is true. If AB is on the graph, so is -AB. Because if you fold it on the y-axis, you're looking at x is A, x is -A, which means one's to the right, one's to the left, and they're both up to point B. Now let's talk about the third function, the cubing function. That is, f of x is equal to x to the third power. And if you graph this on your calculator, you're going to get this graph right here, the middle graph. If you do the table, that just shows you if you plug in -3, you get -27. If you plug in -1, you get -1. If you plug in 2, you get 8, and so forth. Now, f of x equals x to the third increases on its entire domain. If you'll notice right here, it's going up, 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 up. It's always going up. We can draw the entire graph without picking up our pencil, so it's continuous. And then the point at which the graph changes from opening downward, which is right here, and opening upward, which is right here, is called the inflection point. Okay, in a parabola it was called the vertex. In a cubic it's called the inflection point. Now let's talk about a different kind of symmetry. If a function f is defined so that f of negative x is equal to negative f of x for every x in the domain of the function, then f is said to be symmetric with respect to, symmetric with respect to the origin. Okay, what that means is if you have a picture, the origin is through this line right here. If you fold it over, then you would get the same thing. So if we had f of x is equal to x to the third, and then we did f of negative x, well, f of negative x means negative x to the third, which is negative x to the third. And then if we also looked at negative f of x, which means we just stick a negative sign in front of that original problem, so we get negative x to the third here, negative x to the third here, which means this graph is symmetric with respect to the origin. Okay, now in general, if a graph is symmetric with respect to the origin, the following is true. If AB is on the graph, so is negative A, negative B, which means we're changing the x values and we're changing the y values. So we've talked about two different types of two different types of symmetry. So to determine whether the following functions are symmetric with respect to the y-axis, the origin, or neither, we're going to look at two things. We're going to look at f of x, we're going to look at f of negative x, and we're going to look at negative f of x. If these two are true, then we say they're symmetric with respect to the y-axis. If these two are true, then we're going to say they're symmetric with respect to the origin, or it may be neither. We'll see. So for the first one, f of negative x means everywhere you plug in an x, you plug in a negative x. We get negative x to the third minus 4 times negative x. So that would be negative x to the third plus 4x. This sign is different from this one. This sign is different from this one. So these two are not the same. But negative f of x means we're going to change the sign of the original function, which means we would get negative x to the third plus 4x. So in this case, negative f of x is equal to f of negative x, which means they are symmetric with respect to the origin. Now the next one, 2x squared plus 5. Let's check this. F of negative x is 2 times negative x squared plus 5, which is 2x squared plus 5. Now notice these two are exactly the same. Therefore, these two are exactly the same. So this one was symmetric with respect to the y-axis. This one was the origin. Now what about this last one? F of negative x is 5 times negative x to the third plus negative x to the second. So this becomes negative 5x to the third. Negative x squared becomes a positive, so we get x squared. Is that exactly the same as the first one? No. Let's look at this. Let's look at negative f of x. That means negative of the entire function, which is going to make it negative 5x to the third minus x squared. That's not the same as the first one or the second one. So in this case, we have neither. Okay? Next type of basic function is called the square root function, or f of x is equal to the square root of x. Now, for this one, the graph looks like this right here. Why are there no values back here? Because the square root of x is not defined if x is a negative number. So, f of x equals square root of x increases for its entire domain, and it's continuous. But notice that the domain is only from 0 to infinity. Now the cube root function, f of x equals the third root of x, sort of looks like the cube function laying on its side. F of x equals the third root of x, increases on its entire domain, and it's continuous on its entire domain, and it runs all the way from left to right, so we say that the domain is negative infinity to infinity. Next basic type, the absolute value function, f of x is equal to the absolute value of x, which we show that with the absolute value bars. And if you'll remember, the absolute value is never negative. If f of x is equal to the absolute value of x, then we define that by saying it's equal to x if x is greater than or equal to 0. Or it's negative x if x is less than 0. And I know that's a little bit weird, but think about it. If x is a positive number, 0 or a positive, then the absolute value is just that number. But if x is a negative number, then the way we make it positive is we say take the opposite of that negative x. Now, if we want to check this on our calculator, the way we graph absolute value is we go up to y equals, and I think we talked about this earlier, go to math, slide to number. Option number 1 is absolute value, and we're doing the absolute value of x. Now when we graph that, now you may be able to look at that and say, well, if I folded it along the y-axis, would we get the same graph? Yes, so we would assume that this was symmetric with the with the y-axis. Now, another thing we can talk about aside from symmetry is the function can be even or odd. Now, a function whose graph is symmetric to the y-axis is called an even function. A function whose graph is symmetric to the origin is called an odd function. And remember, a function is a relation where each value in the domain is paired with exactly one value in the range. Okay? Consider the relation defined by the equation x equals y squared. It is not a function. How do you know it's not a function? Well, remember we talked about anytime we see a y squared, we need to be thinking, hey, it's not a function, because when we try to get y on a side by itself and we do the square root of both sides, we have to consider two cases. So y is equal to the positive or negative square root of x. Now, look at the graph. Well, the graph of y squared is this parabola that's laying on its side. That will not pass the vertical line test. Now, how are we going to put it in our calculator to look? Well, we can go y equals, and we usually do pretty good on the first one, the square root of x. But then you also have to remember, because this was a square root and we did plus or minus, we also have to remember to do the second case of y equals the negative square root of x. So when we do that and we graph it, there's the square root of x for the first one, there's the negative square root of x for the second one, therefore it's not a function. Now, what would happen if we folded the graph along the x-axis? Well, these two, because one was right above it and one was right below it, and if we folded it along the x-axis, then we would get the same thing. Do you want to think what that's called? Okay, think about it. Determine whether the following functions are even, odd, or neither. Now remember, even was symmetric with respect to the y-axis, which meant f of x is equal to f of negative x. An odd function meant that it was symmetric with respect to the origin, which f of negative x is equal to negative f of x. Now, can you tell by looking at it what's going to happen? There's f of x. F of negative x would be negative 2 times negative x to the 6th minus 8 times negative x to the 6th. So that's going to be negative 2. And negative to an even power is just going to be positive. Minus 8, and negative, that was a 2. And negative to an even power is just going to be positive. We get exactly the same thing. Therefore, this function is even. Let's do the next one. F of negative x is 3 times negative x to the 3rd minus negative x. So that's going to give us negative 3x to the 3rd. Minus a negative is going to be a positive. Those are not the same. This is the opposite sign. This is the opposite sign. So what we're probably thinking is, hey, what if we took the opposite of both terms, which would give us negative 3x to the 3rd plus x? Those are the same. Therefore, this is an odd function. Now, what about the next one? Well, f of negative x is negative x to the 4th plus 3 times negative x to the 3rd plus 1. Have you caught on yet? If it's a negative to an even power, then it's going to be positive. Whereas if it's a negative to an odd power, then it's going to change the sign. And if it changes the sign, it can't be the even function. Okay, so we get that. That's not the same. If we look at negative f of x, that's going to change all of them. So that's going to go negative x to the 4th. That's going to go negative x to the 3rd. That's going to change to, well, actually, that one's not going to change because there was no x. Well, yes, it would. The negative out in front means we're going to change the sign of every term. That didn't match either one of those. So this is also a neither. Now, symmetry with respect to the x-axis. Now, a function cannot be symmetric with respect to the x-axis, but a relation can. Go back and think about this y squared. If that looks like that, vertical line test, which means if you fold it on the x-axis, we're going to have two values that fold on that x-axis, therefore it's not going to work. A relation is symmetric with respect to the x-axis if whenever xy is in the relation, then so is x of negative y. for any particular x value, the y values, one will be positive, one will be negative. Now, to test for symmetry with respect to the x-axis, replace y by negative y in the equation and simplify. If the simplified equation is the same as the original equation, then the relation is symmetric with respect to the x-axis. In general, if a graph is symmetric with respect to the x-axis, then the following is true. If AB is on the graph, so is A negative B. So let's see if these two are symmetric with respect to the x-axis. If we have a y squared and we replace that with negative y squared, we get x plus negative y squared equals 5. But negative y squared is just y squared. Those are exactly the same. So yes, this one is symmetric. Now remember, it's not a function, but it's a relation that's symmetric with respect to the x. What about the second one? Well, we're going to replace y with negative y. So we get minus a negative y equals 7. So x to the third plus y equals 7. Not the same as the first one. So we would say that no, this one is not symmetric with respect to the x-axis. You are now ready to complete this section of homework in my math lab.